Welcome to today's developer community meeting. I think this is number 7. Appreciate you guys joining. Today is going to be a lengthy one. We have a lot of content to cover, so we'll go through our first slides quickly. Just a quick agenda. We'll quickly remind you that we have a discourse that you guys should enjoy, and then we'll jump right into the Cerebras Wafer-Scale Cluster and our Appliance Mode. So if you haven't joined already, strongly recommend that you join our discourse. You can find it at discourse.cerebras.net. There's a lot of conversations here. Feel free to use this as your opportunity to communicate with Cerebras, especially Cerebras engineering. Yeah, if you have any questions about this, please let me know. And without much further ado, we'll pass this on to Saumya and Claire, who will give their presentation today on the wafer-scale cluster and our appliance model.
All right, thank you, Uday. Thanks everyone for coming to our meeting today. We're very excited to talk about Cerebras Wafer-Scale Cluster and Appliance Mode in today's meeting. To set the stage for today's talk, we have been observing an exponential growth of neural networks nowadays. Back in 2018, we have BirdBase, which is 100 million parameters, and it was a lot at that time. In 2019, GPT-2 and Megatron LM are announced, and then we're now in the billions of parameters regime. In 2020, we got GPT-3, which has 175 billion parameters, and also the empty analogy model, which goes up to 530 billion parameters. This is a big jump. Within 2 years, we are observing 1,800 times more compute, and that is a very large number. Tomorrow, we may want to try multi-trillion parameter models. This is a very daunting task, but also very exciting. However, the trouble today is that the traditional approach has been facing a lot of challenges to scale out. We can take a look at what they are today. The simplest one is data parallelism. Essentially, you put a replica of the model on each of the device, and then run data parallel training. The problem with that is that under the parameter memory limits, large models may not be able to fit on one device. For the second option, pipeline model parallel training, you distribute the layers and run different layers on different devices. However, this approach suffers from communication overhead, and the activation memory will increase quadratically. The third option, tensor model parallel, means that you have to partition the layers onto different devices. This is a very complicated process, and also it suffers from communication overhead. All of these 3 methods share the same limitation behind the scene. That is, their memory is tied to the compute. Nowadays, if you want to run parallel training on GPU clusters, if you have done so, you'll know that it's a very complicated practice. On the figure shown on the right, along the x-axis, we're seeing the increase in model size over time. And on the y-axis, we're seeing that the larger the model, the more nodes, the more compute nodes you generally need. And you will start to need a hybrid of different kinds of parallelism at the same time to run the massive model training. For users, it results in complexity in practice, and also the compute often results in poor scaling. To tackle this problem, Cerebras actually offer a very elegant solution to that. Today, we'll take a sneak peek into okay, Alfred has a question. How massive is massive? Think about if you want to run like GPT style billions of parameters, it would be very hard for you. You have to like run these parallel methods to run on GPU clusters, and you have to think about different parameters, how you maneuver between the compute you have. So that's a lot of choices to make. Also, like, feel free to put your questions in the chat. I'll be monitoring the chat while I'm talking. Okay, speaking of Cerebras solutions, so we'll take a sneak peek into how we build our compute to scale out from 1 to n CS2 systems. Here is a figure of our 16-box Cerebras Wafer-Scale Cluster. It's a massive piece of equipment, but for developers, it's actually quite easy for you to interact with and run jobs on the system. And now I'll quickly show a demo just to give a feeling of how it, as a developer, how you would be interacting with this piece of equipment. Say you want to run a training job, you're not at your console, and you want to use one CS system to run a training job. This is a GPT-2 model training. You type in this one command and then specify that you want to use one CS system. Now the compilation will start, and then what follows, the training will start. And then you want to use 4 CS systems to run your training job. You put in a very similar command and you just change this number to 4. And then the progress is very similar. You observe that the compilation starts, and then the training will start. And similarly, if you want to run 8 systems, change the num-CSX to 8 on the same command. And you'll see that compilation finishes and then training starts. So the progress printout will show you the throughput of the training that you're running on the right. This throughput number is per CS system. And you can see that regardless of the number of CS systems that you're using, this number actually remains about the same. And that actually what gives us linear scaling when it comes to our multi-system cluster. So far, we have tested different GPT models of different architectures, different sizes, and different sequence length. And we have been consistently observing linear scaling from 2 nodes to 8 nodes. This is a very remarkable result. And so now Saumya will take over and then introduce the technology behind of how we achieve these amazing results. Saumya.
Hey, thanks, Claire. So now that you all have seen how simple and easy it is to scale from 1 CS2 to 8 or 16 or all the way up to 100 CS2s by changing a single parameter, and at the same time, you can also get the benefit of the near linear scaling, which has been a challenge in the market today. Let's after seeing the cool things, now let's deep dive into some of the aspects on how we achieve that, what are our key components, and is it really that simple from a user perspective, or do user have to do more than what was shown in the demo? Let's dive in. So here introducing the Cerebras Wafer-Scale Cluster. Cerebras Wafer-Scale Cluster is our entire gear, the hardware gear, where we combine multiple CS2s and provide a way to scale from 1 CS2 to more CS2s as part of your deployment. What it consists of is 3 different parts. One is the MemoryX. I'll get a little bit into details on these. SwarmX, multiple CS2s, and finally, any input pre-processing, any servers needed for that. The actual data storage for training data is outside of the cluster. If you remember, the CS2s can be 1 to n, but the main challenge that Claire spoke earlier was that the memory and the compute have always been combined together. They've been together. And that is the one which poses the challenge to make the near linear scaling in performance extremely challengeable. And that is the one which also brings in all the complexities of distributed computing. Enter MemoryX. We can go to the next slide. So with MemoryX technology, what we have actually invented here is a way to disaggregate memory from compute without having to suffer from a performance penalty and still be able to enable all the way up to trillion parameter models. So if you take a look at the diagram here on the right, MemoryX is the one which stores all the weights of your model externally, and it's a separate hardware which is disconnected from the actual wafer scale engine, which is our CS2 system. So the weights are streamed into the CS2 over a low latency fabric. And we have done tons of optimizations to even further camouflage or hide any latency related delays with handling the pipeline way of how the weights get updated. Now, once the weights are streamed to CS2 does all the crunching, and it is super fast. It's a huge wafer scale engine. And once it finishes crunching all the numbers, the gradients are streamed off the wafer into the MemoryX. MemoryX is the one which does the any kind of optimizer compute that is needed, adjusts the weights for the next layer, and then each layer is executed at a time on our CS2. So with this approach, while the memory and the compute is being disaggregated, there's also the advantage of being able to run one entire layer without having to do any layer sharding completely on our CS2s. The activations themselves are resident on the wafer, so there is not any additional price to fetch the activations. However, the activations are being fed actively through the servers that are used for input pre-processing. And we have different techniques to ensure that they are not bottlenecked, and the CS2 itself is not starved for data. So with this, we are able to support models with trillions of parameters at great performance, like you saw, which is, again, what has been very challenging in the current state of the art market solutions. So that was more about single CS2s. Now we have to easily scale from one CS2 to n CS2s. And for that, we introduced something called as the SwarmX technology. SwarmX is another hardware piece that we have introduced, which is a very simple piece of hardware which takes the weights from MemoryX, sits between MemoryX and CS2, and does all the weights broadcasting to all the CS2s. And when CS2s are done with their crunching and gradients are ready, it reduces the gradients back into MemoryX. So everything is handled very seamlessly by our interconnect technology here. With this, the multi-system scaling with same execution model as a single system is made possible. So it's the same system architecture, same network execution flow, and the same software user interface, but you're able to easily scale from one CS2 all the way to number of different CS2s, depending on your use case, your workload, and you do not have to worry about reprogramming or sharding your layers or doing any other aspects that are needed with distributed computing. So compute is really scaling here, independent from the capacity. Okay, so that is more around the hardware piece of it, the actual cluster that goes and gets deployed onto your data center. Now let's look at how it actually interacts with the appliance workflow. So what, from a user perspective, the actual user workflow looks like.
Hey, Saumya, we have a question from Alfred. He's asking, what is SwarmX?
Yeah, maybe we can go back to that slide. So SwarmX is a piece of hardware. It is an interconnect. It's a hardware that has technology to handle multiple interconnect switches, such that the main functionality here is to do broadcast and reduce. So it takes the weights from MemoryX, and since it interconnects multiple CS2s, it's able to broadcast the weights, and then on the way back, it collects gradients from CS2s and reduces it. So if you're familiar with broadcast and reduce in the collective communications aspects of distributed computing, so all it's doing is broadcasting to a number of CS2s and then taking the gradients from all the CS2s, reducing it so that it goes into the MemoryX.
Hey, Alfred, did that help answer your question?
Yes, thanks.
Okay, so it all looks good from the hardware perspective, but what about as an ML user? As an ML user, you really do not have to care about either MemoryX or SwarmX or anything that's happening inside the cluster. So what you would really be looking at is our whole wafer-scale cluster running as an appliance. So you do not think about individual pieces and make any code changes or any scripts or any commands specific to your particular configurations of these hardware pieces. All you'll think about it as a big black box, as an appliance, and you just program to it directly. So as an ML user, the wafer-scale cluster will appear to you on the network as a training service. You'll submit a job and the appliance will produce the result. That's all you care about. And the underlying software components, even including anything to do with orchestration, how the different hardware pieces are managed, how the work is transferred to CS2s, and all of that scheduling and managing and orchestration related aspects are all hidden under the hood by this appliance model. From a data center admin user point of view, Cerebras assembles all of this as an appliance at the user side. Cerebras software will manage all the internal resources of this appliance. This includes operating systems on both the user node and the cluster, the orchestration pieces, like I was highlighting earlier, the MemoryX software, the SwarmX software, all that broadcast, reduce, and all of that stuff that I was talking about, and the entire wait streaming execution stack that will be utilized to make this magic happen. But all of that is again managed through the internal resources, and neither from the sysadmin side nor from the ML user side need to worry about any of this piece of software. The user interface itself with the appliance will be managed through an API, a Python interface, and user is not expected to think about any of these internal components. Okay, so then what does the user do? So user will program whatever is on their TensorFlow and PyTorch script. So they go through our similar programming practices of what your native TensorFlow and PyTorch scripts are. There are minimal steps, which some of you might already be familiar with if you've used our system before, on how to port the models and make them compatible to run on CS2s. And we have extensive documentation about it. So none of that is changing just because we're bringing this huge cluster and additional pieces of hardware. So once you program your TensorFlow or PyTorch script, it will just run on the user server, which is external to the which is external to the appliance. So each user will have a user node with user server. So the program will just run there as if you're running on a single device. The user server itself needs very minimal client software. So the client software like installed on the user server, like the Python package, any Python dependencies that you have, you'll have your virtual environment and you can just install your Python packages into that. This is not Cerebras stack. This is the virtual environment with all the required libraries that you would use as a typical ML user. Then the stack or the compile itself will run this in appliance mode. The client software will only provide a thin wrapper to submit the job to the appliance. So from a user perspective, you can almost think of as there's not much change that you would have to do for your TensorFlow and PyTorch script and any of the other Python libraries in your environment that you have been using, but only think about this thin wrapper where you submit the job to an appliance, and once the appliance is done with its processing, you receive the result back. So this is very similar to how you would think of it as a local GPU run. But just instead of running on a local GPU, you'd actually be running on a cluster of CS2s, which can range from 1 to many clusters. User can run this program as though they're training locally. The job is submitted in the background, and you can still continue to do your other workloads. The results are always routed back to the user, so you don't have to go or get into the appliance or software or into the cluster itself. So you can send a job to 13 million core cluster here, which is our huge hardware, with the ease and simplicity of sending it to a single GPU. This image here gives a sneak peek into how the topology of our whole wafer-scale cluster and appliance looks like from a weight streaming execution point of view. As I was talking about the thin wrapper on the user client side, that's what resides to the far left, which is external to the appliance. And the user runs their Python code. For example, here we call as run.py. So they use their Python code, their Python script, and submit a job to the appliance and receive the loss and any updated tensors and whatever results that they are expecting back. And that's pretty much the interface that the user has to do. But what comes inside appliance is the very first step of multiple servers doing input pre-processing for all the input data. There's a management node. Again, all the internal orchestration management for our appliance is through Kubernetes. But again, it's internal to appliance and user doesn't need to know anything about the Kubernetes here. So the management node will manage the MemoryX as well as the SwarmX. And with MemoryX, it will work through the weights and the activations, while with SwarmX, it works through the functionality of broadcast and reduce functions that we discussed earlier. And finally, different CS2s, depending on what the user would have asked, whether they want to run their workload on single CS2, 2 CS2s, 4 CS2s, or n number of CS2s, and how those CS2 resources are managed is all part of our appliance inside. Now there's a natural question about multi-users because this is a huge hardware cluster and it has the capability to scale from one to many CS2s, but workloads can all vary. Some workloads or some users might need 1 CS2s versus a few others might need 8 CS2s, or some might even need all the way to 16 or 32 CS2 clusters. So it all depends on your workload and use cases, and you would want to enable naturally multiple users leveraging this behemoth of a cluster. So that's exactly what we provide here. So multiple users can run on the cluster at the same time. So you can view this, the example here is more like an 8-node cluster. So you can view this 8-node cluster as either 2 4-node clusters or 1-node cluster, like 8 1-node clusters. So literally like running a different job, a different workload on each of the CS2s. Or it can be any combination, like a 2-node cluster and a 1-node cluster that user 2 and user 3 are using here. So it can be any combination within that. But the beauty of it all is, from a user perspective, user only needs to tell how many CS2s their workload would need. They do not have to think about which CS2s, how they are available, whether a CS2 would be sufficient for that. So all the distribution of how this is handled inside appliance software, and that's completely abstracted out from the user. So what are the advantages of appliance mode in a nutshell? This makes interacting with millions of compute cores as simple as running the application on a laptop, as though you're running your training locally using a single GPU. It has the most familiar developer-friendly Python-like workflow, which can launch job from anywhere. And we're working on use cases like being able to include a Jupyter notebook and launch job from Jupyter notebooks. The beauty of it is, from an ML user perspective, you do not have to think about Slurm, Docker containers, Kubernetes, any orchestration, any infrastructure, MemoryX, SwarmX, or whatever we have inside the cluster and the appliance software. For sysadmin, even though the cluster has all these elements, they're all managed as a single appliance and pre-built and provided by Cerebras. So it should be extremely simple and easy to deploy our whole cluster as is onto your data center. Redundancy and resilience are built in with this appliance workflow. Any failover is handled dynamically within the appliance as well. If a CS2 fails, for example, that's handled dynamically within the appliance. And it provides easy multi-user experience, multi-user use case, where user has to just specify how many nodes they want without having to think about any internals of making those nodes available. But just to give you an idea of how complex all this appliance software is, I think this one slide captures all the software processes under the hood of appliance, which is completely hidden from ML users. So from hardware perspective, like we have spoken extensively now, has multiple different components from pre-processing servers to MemoryX, SwarmX, and the actual CS2s. But when it comes to the actual software processing, we have our weight streaming stack, where you have the framework layer of handling TensorFlow, PyTorch, their different libraries, APIs, and different modes and all that. But apart from the framework piece, there's also the input pipeline, which is extremely crucial here. Data loaders and how you would use the input pipeline in order to feed into the CS2 and not bottleneck or starve CS2s of data. At the same time, all the stack around compilation, like how the conversions happen, how we map, how we utilize some of the advantages of our multi-million core Wafer-Scale engine. And what that reduces or uses in runtime is our handwritten high-performance kernels, along with any client I/O software or the wait server, activation server, and so on. So all that comprises of the weight streaming software stack. And at the very end, the cluster management piece, which is mostly to do with how the whole cluster itself is managed, right from user job interface, such that ML users can only do the submission of the request and receive the results, all the way to how the management of different components need to happen. Any orchestration, the failure recovery, and the monitoring, and all of that is also handled under the appliance and under cluster management. So all these different pieces are what's actually happening under the hood of appliance software. Today, from a user perspective, since this is all hidden, we're not going to go into details of this, as there's no need to know. I want to give a quick overview on how this looked and what all has been hidden from the user perspective to make the workflow easy and hence drag this in. Okay, so that is more about the hardware and then the software, the workflow piece. Now let's see what and how is this actually achieving the strict data parallel scaling, which all ties back to how your near linear scale performance, which is what you actually care for, is being enabled. So wafer-scale integration, the whole stack, is what is the foundation for strict data parallel scaling. MemoryX, as you saw, is being disaggregated from the compute, which is CS2 itself. And this sheer disaggregation gives us a lot of freedom to choose flash memory or to choose different technologies here for MemoryX so that the memory itself can be scaled separately from the compute. Because our Wafer-Scale engine has 850,000 compute cores, this is the latest Wafer-Scale engine 2, which is on CS2. Now, this can handle the largest of largest matrix multiplications. That means there doesn't have to be any use case where a single layer need to be split across multiple CS2s. Our Wafer-Scale engine is so huge that it can fit the largest of layers of the largest NLPs, even handle matrix multiplications about hundreds of times larger than today's state of art. So going forward, many years from now, also you will be able to just fit the whole layer on the whole onto our Wafer-Scale engine and do not have to worry about the hybrid parallel model where you would be splitting the layers. The Cerebras never needs to distribute matrix multiplication over multiple CS2s. So it's always one layer on one CS2s. So this allows Cerebras to go with the very first approach of parallelism that Claire introduced, which is data parallel approach, which as an ML user, you might already be familiar that it's the most simplest and the most easiest way to scale out. Now, MemoryX enables Cerebras to have memory to support all these largest models. SwarmX enables to scale out from one to multiple CS2s, but they both together enable strictly data parallel scaling. Now, with data parallel scaling means you just take the data from outside and distribute data into multiple CS2s. So that means you can easily get the scaling which in performance, which is linear or near linear, like the performance table that we saw. So it's all part of the entire solution of what we built. So let's take a look how this is done. So all that is happening here is we put the same image on each CS2 in the cluster. We divide the data set into multiple parts and send each part to each CS2, then start training. So this is the version where 2 CS2s are used. Let's move on. So this is the version where 4 CS2s are used. Again, all we do is from the input pre-processing, we divide the data into 4 parts now and feed it into the CS2s and start the training. Next slide. So this is where it just expands into 8 CS2s. So this keeps going and it can go all the way from 8 to 16, 32, or 96 CS2s. Next slide. So just to summarize there before I hand it back to Claire, is that it's clearly what helps us get to that near linear scale performance is how linearly we are able to scale from one to many CS2s by just splitting the data and putting them on different CS2s. But beyond that, we do not have to split anything else, be it multiple layers or be it a single layer split across multiple CS2s. All the other parallelism models need not have to come into picture with our design. And hence it's strictly data parallel. Over to you, Claire.
Yes, thanks, Saumya, for the very interesting technical deep dive. Now let's look at for developers, what's your job interface is like.
Hey, Claire, I'm sorry, real quick to interrupt. Looks like Alfred has a question. In some figures, inputs are fed to MemoryX, but in other figures, inputs are fed to the CS2. Why is that?
So maybe I can help take that. So the activations are fed directly into CS2s, while the weights are stored in MemoryX. And with our pictures are still more symbolic versus actual flows. So that's the reason we vary based on what message we are trying to convey in that particular slide. But overall, as you can see, both the activations and the data itself goes into CS2s. But the weights are the ones from the training from the initial version of the trained model that goes onto the MemoryX.
And it looks like MN has a comment. As far as I understand it, it's only data parallelism, right? We don't need to apply model parallelism.
Yes, you do not. So other than initializing your trained weights, you do not have to worry about any model parallelism. So it's strictly data parallel. So you split up your data and spread it across different CS2s and start your training. And everything else, like how the trained weights are going to MemoryX, coming back from MemoryX, getting updated, is all handled internally in the Appliance software.
Alfred, did that answer your question? Looks like MN that answered yours.
Yes, I think what I figure is that is just a matter of presentation for the sake of giving the talk, right?
Yeah, that's correct. And just in order to orient the whole flow, we have and what point to highlight, we have kept them more symbolic.
Thank you.
All right, cool. Let's continue. Okay, in order to run your jobs, there are a few short preparation setup steps that have to be completed. First of all, the administrator have to prepare the appliance, set it up. But for users, there are 3 steps. First, you need to make sure that you have a TLS certificate for authentication so that you can work with the appliance. And second, you will need to set up a virtual environment with Python 3.7. Within this virtual environment, for step 3, you will need to install some Python wheels. You need the Cerebras appliance package to interact with the appliance. And depending on whether you're using TensorFlow or PyTorch, you will need to install the Cerebras TensorFlow wheel or the Cerebras PyTorch wheel. And you just need to pip install them in the virtual environment. There are a few modes that users can run: compile, train, and eval. So within your Python environment, and after you have navigated to your model directory, there are several things you can do. With this command, and specifically with the flag validate only, you can do an initial compilation just to understand whether the model can be lowered to the hardware. And with the compile only flag, you can do a full compilation to generate artifacts for training. With the mode set to train, you can do training jobs, and with the mode set to eval, you can do evaluation jobs. And then within the model directory that is specified in your command, you'll have the outputs and artifacts. More specifically, you'll see checkpoints, TensorBoard event files, and also a configuration YAML file. And now you're all set to do training jobs. It will be just push button easy for you because we're only using data parallelism in our cluster. To reiterate, you've seen that during the previous demo, the way you configure a run on single CS2 is just to put this command in your console, for example. So there are a few arguments. Python run.py launches the Python script. Param.yaml is your parameter file in the model configuration, data configuration. num.csx is how many CS2s in your clusters that you want to use. Model directory is where you want to store the outputs. Number of steps is the training steps that you want to run the model for. And mode specify what kind of task you want to do.
Hey, Claire, sorry to, oh, looks like Alfred says never mind. Please continue.
Okay. So that was for work on one CS2. If you want to distribute work over 2 CS2s, you just change the num.csx number to 2. And then change this number to 4 if you want to distribute work over 4 CS2s. And then 8 and 6, with just one simple keystroke and number change, you'll be able to distribute work on 1, 2, 4, 8, and 16 CS2s.
Hey, Claire, we have a question from Anirudh. Is Python -ws run.py discontinued for weight streaming?
Yes, if you're running in appliance flow, the appliance mode that we're introducing today, yes, I think Python -ws run.py is discontinued. Saumya, could you confirm as well?
Yeah, exactly. And if you go back to 1.5, you should still be able to run Python-ws and run the weight streaming models on our pipeline cluster, the CS2 with 9 worker nodes, if that is what you're familiar with. But with the wafer-scale cluster, the way to run weight streaming models is through this appliance workflow. And that is what brings the new run appliance.py. Or the run.py.
I see. Thank you.
Cool. Okay, so that is an overview of our Cerebras Wafer-Scale Cluster and the appliance flow. If you want to get hands-on and get started, please visit our Cerebras Model Zoo. This is so Cerebras Model Zoo is our public repository. Go to this link and you'll see our reference model implementations, and we provide multiple configs for each model to cover different variants. There are different documentations, for example, for data loader as well. And also, please visit our developer documentation webpage. This is a very comprehensive reference materials that contains from conceptual guides to step-by-step tutorials of how to do runs, best practices of using our system, release notes, common questions, and more importantly, it's searchable. If you are curious about certain keywords, just type it in and you will find your answer there. This is very comprehensively written, and I'll highly recommend just taking a look. And specifically to run Appliance Flow, there's a getting started guide at this link. If you're interested, please take a look. To learn more, we also have technical blogs on our website introducing Appliance Mode and how we achieve linear scaling, and also the wafer-scale cluster setup. We also have our release notes on our Cerebras documentation page that I just introduced. Most recently, we released our software version 1.6.0. If you go to this link or our documentation webpage, you will see the details of what progress we have made and what we're up to right now. A lot of exciting things going on over there. And then if you want to get help from our experts or from your fellows, please use our Discord channel. On this platform, Cerebras engineers will be able to answer questions, and also the community will also post questions and answer questions there. If you want to get in touch, please use this email, developer@cerebras.net. And if you want to learn more about developers community, please visit this link below. Thank you very much for listening to this talk. If you have any questions, please feel free to unmute and ask.
Yeah, I just have a general question. So compared to a typical GPU like A100 or something like that, how much bigger a model you can fit on CS2? Is it 100 times that, 1,000 times, 10,000 times? Just want to get a feeling for it.
Saumya, do you want to introduce what's the largest model we can train on one CS?
So if we're looking at fitting the whole model on a single CS2, it's typically around 1 billion parameter model. So we would say something to the range of medium-sized models up to or less than 1 billion parameters. You can use our older pipeline mode of execution that you're probably familiar with, which puts the whole model onto the wafer-scale engine and streams activations from outside. But when you're scaling beyond 1 billion parameters and going into the realm of these extreme scale models with GPT-3, GPT-J, or even the full-blown T5, that's 11 billion parameters and so on, that's when the whole model doesn't fit on our wafer scale, and hence the design around the wafer scale cluster with MemoryX and SwarmX, where you would still fit the entire layer, so you do not have to do any layer sharding, but you would be able, you would have to, you cannot run the whole model or fit the whole model onto our wafer scale cluster. But again, when there's no simple or direct comparison with GPU to say 10x to 100x, but mostly the way we measure is with respect to how big the model is. And we generally say anywhere like the medium scale models from 600, 700 megabytes to all the way to 1 billion will be the more efficiently utilized if they are completely fit on our wafer scale engine and used pipeline model, right?
Just want to check this to make sure that I'm hearing the right things. Do you say that Cerebras can partition the model automatically without us getting involved by virtue of letting it happen in MemoryX?
Yes, because the whole execution flow is such that it takes one layer by layer and maps the whole layer onto the wafer scale engine. There's no need for an ML user to get involved in which layer goes or how much of that layer goes onto the actual hardware. So all you would need to feed it is the data and the model, and then the rest is taken care of internally.
Right, and also Saumya, could you introduce like was this layer by layer, as we call it, wave streaming execution? What's the largest model that we can train right now?
So right now with 1.6, we have included early access to up to 20 billion parameters, but technically or theoretically, we can train much larger ones. And we're working towards that to make sure we validate some popular variants that are already published in the market so that we can provide configs for that. But ideally, you should be able to run much higher. Currently, up to 20 billion is what we have been validated internally.
Is it scalable? So if you multiply the number of CS2 by a factor of 10, can you handle 20 billion parameters?
Today, what we have been validating is on the performance side. Like for example, you fit the whole layer with 1 CS2 to 4 CS2, you will get more closely 4x. So if you go back to the performance table, maybe Claire on your earlier slide. All the way to the performance table. Yeah, slide 11. So if you look at this here, the way we are distributing the processing itself, we see that from 2 node to when you increase to 4 node, the same GPT-2 1.5 billion model can run at 4x instead of 2x, right? More closer. So that's the linear scaling that we were talking with respect to performance. Now, in order to run from a 20 billion parameter to a 40 billion parameter, again, each model might bring different challenges with it, and we are working internally to validate or do enough QAs and variants, QA on the variants before we claim official support for that.
Yeah, looks like we've got all our questions answered. Saumya, Claire, thank you so much for presenting today. To the attendees, thank you for joining. As always, if you do have additional questions afterwards, please don't hesitate to reach us out at our developer@Cerebras email or by posting a question on our discourse. If you do want to share a recording of this, please do note that we'll post the recording of this on our discourse as well. And so, yeah, with that said, thanks everyone for joining, and we'll see you next time.